So hash tables, not just for breakfast anymore. That doesn't really make sense, just like the previous one. Thank you. It's not particularly witty or anything. Hash tables, let's talk about them. So hash tables, you've used it a bunch already, and you're going to implement your own, so pay attention. You've used them with the dictionaries. Python dictionaries are internally actually hash tables. So what do hash tables do? They map keys to objects. So for the word "the" in your corpus text, you can see that it appears 10,026 times. So it maps the key "the" to the value of 10,026. So dict is a hash table. Hash tables are used because of strong average case performance. So in particular, we'll talk about this in a bit, but the ability to access an element in constant time is super important to hash tables. So this is kind of what a hash table looks like. Basically, you have your keys, which are then run through a hash function. The hash function converts your key into an integer. We'll talk more about how they work in a second. And then you have these buckets. So based on the result of the hash function, your key gets assigned to a different bucket. So here we can see that the key John Doe got assigned to bucket 3. The key Jane Smith got assigned to bucket 0. The key Lorem Ipsum got assigned to bucket 2. And Kenny G, he's in bucket N, which is like the last bucket. So what are these buckets? Generally speaking, these buckets are an array. So we just talked about arrays at the beginning of the linked list section. Generally speaking, these buckets are arrays because it's very nice to be able to access the buckets in constant time. Actually, that's sort of like the fact that these buckets are implemented as an array is part of the reason, it's like a big part of the reason why you can get constant time access for any kind of key in a hash table. So what is a hash function? A hash function is like super important in computer science and in just like general programming. A hash function converts any kind of input. So like any size of input, could be a string with 1 character, could be a string with 10,000, could be an integer, could be just some class that you implemented. A hash function will convert that input to a fixed size output. So in this example, John Doe gets converted into this number 512,340. Jane Smith, 408,749. Basically, it takes an infinite range of input and converts it to a fixed range of output, which is like a super important property. Another super important property is that if you put the same input into the hash function, the output will always be the same. That's vitally important. Yes, Ignat. This is a great question. He's anticipating the next slide. Can there be 2 different inputs that map to the same output? The answer is yes. We'll talk about why in a second. So the input can be anything, can be a string, a pointer, a custom class. But all this input, like the infinite possibilities of input, map to a fixed range of output. So let's talk about the ideal hash function. The ideal hash function is repeatable. That's that section where we said the same input should generate the same output every time. An ideal hash function is fast because, for example, in our hash table, we're going to be doing this a lot. So we want our hash function to be able to calculate the output value very quickly based on the input. The ideal hash function, the output is an unsigned integer. So remember, we can take any possible input. It all gets mapped to an output number on this number line. So your hash will result in a number anywhere between 0 and, in the case of a 32-bit unsigned integer, 2 to the 32 minus 1. So that's like a possible range of like about 4,192,768, something like that. So the ideal hash function randomly distributes keys among the output space. So you could create a hash function that for every single input returns 0. That's a hash function. It satisfies these requirements. It's repeatable, it's fast, the output is an unsigned integer. But that will create a lot of problems when you try to implement your hash table. So the ideal hash function distributes the keys among the total output space. So returning 0 for every input is kind of like a silly example, but what if we had one where, because of the algorithm used in the hash function, most of this number line goes unused and it only returns even numbers. So that means half of our possible output space is never used, which is not good. Ideally, it randomly distributes the keys among the whole output space. So also, small differences in input should result in large differences in output. That way, if we're storing a bunch of strings and say a bunch of them are very similar, they should not result in the same hash number. Like, for example, if we hash dog and we hash dogs, we don't want them to end up in the same hash number, the same output value. We want them to be drastically different. So Ignat asked, does that mean that sometimes two completely different objects will hash to the same output? And the answer is yes. There's no way that's not possible because there's a fixed amount of possible output, which in this case is a number between 0 and 4,192,768. So that means there's an infinite possibilities amount of input, a fixed amount of outputs. That means some inputs will have to match to the same output. There's no way for that not to be possible. So that's something that's unavoidable in hash functions, but as we'll see in a bit, there's ways around that fact. You can sort of work around that to still create your hash table and have it work very well. So hash functions are used everywhere. Oh, and by the way, there's this little asterisk up here. This says at the bottom that this is different for cryptographic hash functions. So these are the requirements for an ideal hash for like a hash table. For cryptographic hashes, you have a totally separate set of requirements, things like security, and the hash should not be reverse engineerable, all these other things. So hashes are a one-way function. We can take an output, we can take any input and generate an output, but we cannot go the other way. We can't take some output number and regenerate what the input was. There's way too much data lost to ever be able to do that. So hash functions are one way. So there's a lot of really cool applications of hash functions that can do really powerful things. For example, Dropbox and other similar cloud syncing services use hash functions all over the place. For example, if I bought a movie on iTunes and it's like a 10 gigabyte file and I save it in my Dropbox because I want to back it up, Dropbox has this crazy optimization where it will take a hash of that file, generate a unique key, and then it will check if anyone else in the world has saved the exact same file in Dropbox. And if they have, instead of re-uploading the whole 10 gigabytes, it will just assign a pointer in my account that will point to the object. So they don't have to save the same movie 10,000 times for everyone that bought the new Mission Impossible movie and stuck it in their Dropbox. They only have to save one copy plus a couple of backups, and every single person gets access to the same exact copy, which means other than the first person to upload it, no one else had to actually upload those 10 gigabytes to Dropbox. Does that make sense? Yeah, Adrian. So what happens when it's removed? Well, if someone deletes that item from their Dropbox, Dropbox checks and sees that 9,000 other people still have a pointer to that item. So it doesn't actually get deleted out of the cloud, just your reference in your Dropbox is removed. So that's crazy, right? That saves you a ridiculous amount of time. Yeah, Ignat. What if the original person that uploads it deletes it? This is sort of an implementation question. As long as Dropbox is not buggy, they will still see that 9,000 other people have a reference to the file, and it'll stay there. Yeah, Adrian.
So you don't own the file.
Yeah, so you don't actually own the file. It's kind of like a shared common file. But if you were to make a change to the file, like if you were to add if you were to cut the last 30 minutes off the movie, suddenly the hash function that's run on the file will result in a different hash. Dropbox will now see that you have a completely unique file that no one else has, and it will upload the whole thing. Yeah, David.
In terms of iTunes, though, wouldn't it also give you different hash because of DRM?
So I used iTunes. The real example is if you pirate a movie, and then you stick it in your Dropbox, and everyone else pirated the same movie. iTunes might be a little bit different. iTunes might have custom DRM for every file that's downloaded. Although, like for example, if you buy music, iTunes Music has been DRM free for like the last 7 or 8 years, so you're getting the same file as everyone else. So when you store all your music in Dropbox, it doesn't have to re-upload it all. It just takes the hash, sees other people have the same file, and assigns your account a pointer to that same file. So there's other really powerful things you can do with hashes too. The Bitcoin blockchain is largely based on hash functions. One really cool thing you can do, let's say, for example, you have a will, and all your inheritance, everything you want to have happen when you die is in your will. You can take a hash of that document and store that somewhere. And that way, when the executor or your lawyer is going through the will, they can compare that version of the document to the hash to see if any changes were made. So hashes on any kind of document give you a tiny little snapshot that can allow you to prove whether or not changes have been made to it. Because remember, the ideal hash, a small change in the input results in a drastic change in the output. So if you have a document, you change a couple words or even one character, the resulting hash will be different, which means you can prove that the document was changed. So this is kind of like a really cool idea where Bitcoin comes in, and that's a whole other subject. But very briefly, Bitcoin is like a distributed, decentralized database. So you could take a hash of your will or any legal document, you could save it in the Bitcoin blockchain, which would mean it's stuck there permanently forever and that it exists in hundreds of thousands of computers around the world. And then you can prove later by going and looking at that hash if the original legal document was changed from when you saved it. So that's just like one small application of hash functions, the other one being Dropbox, and there's a ton more. A huge amount of cryptography is also based on hashing. Yeah, Ignat.
I see sometimes when they have download applications where you take a source from GitHub, there's something called like MD5 hash or checksum or something.
Yeah.
Is that
So MD5 is a kind of hash function. There's a bunch of other ones like RSA 2048, RSA 4096. There's a ton of different hash functions. MD5 is a very simple one that works to help you prevent corruption. So if you download a large file, very often it will come with a MD5 hash of that file, and then you can, on your local copy, also make a hash of it, and you can check to see if the file was corrupted at all during the download. So it's also used for security. So when your computer gets an update, it says, hey, new version of OS 10 is available. Download it. The App Store will download it, then it will take a hash of that whole thing it just downloaded, and will compare it to an official hash from the Apple website. And if it finds that the hash is different, then it knows either that the download was corrupted or some malicious person is trying to get you to download like a fake version of your upgrade, and it won't install it. It'll delete the whole thing and try again. So you can kind of like prove whether or not a file was tampered with hash functions. Okay. So now let's talk about these buckets. So remember, these buckets are an array, so we can index into them in constant time, and we're going to store the things that we hash for our hash table into the buckets. So we'll take the key, take a hash of it, and then store the value in a bucket based on the hash of the key. But how do we decide which bucket to stick our item in? Well, it's actually a very simple equation. You take the hash of the key, and then you do modulus n, where n is the number of buckets you have. So who wants to explain what the modulus operator does? It looks like a percent sign in most programming languages. Yeah, Andre. Returns the remainder, right. So if we have 8 buckets, modulus 8 will divide the resulting hash number by 8 and then tell us what the remainder is. So if the hash like mapped to for example, I don't know, 17, and then we did mod 8, it would divide by 2 twice, and then the remainder would be 1. So 17 mod 8 is 1. So why do we mod the number of buckets we have? Why are we doing this operation? Yeah, David? Exactly. So we might have 8 buckets in our hash table, but the hash function could generate a number between 0 and 4 billion something. So we need to be able to map that range of numbers into the smaller number of 8 buckets. So by taking some random huge number, modding by 8, we guarantee that the result will be between 0 and 7, which will mean that it's a valid index in our buckets array, which means we can store it. So that's a cool thing. Any number mod the number of elements you have will result in a valid index. So let's talk about collisions. If we have a hash table, you can have a hash table with thousands of buckets, with hundreds of thousands of buckets. You can have a hash table with 8 buckets. Most hash tables, when you first, like even the Python dictionary, when you first create it, I think it's created with something like 8 buckets. It might be 16, but it's like some small number of buckets is created when you first initialize a Python dictionary. So then what happens when you get multiple items mapping to the same bucket? Well, when that happens, it's called a collision, and there's 2 main ways that you can resolve this problem. The first, so again, it's impossible to map all possible input to a fixed output space without there being collisions. It's just not physically possible. So differing input generating the same output is called a collision. So the first way you can fix it is called linear probing. So each bucket contains 1 object. If you get a collision, you go to the next open bucket and add the object there. So for example, in this case, John Doe mapped to bucket 1 because we took the hash, we did mod the number of buckets, and it happened to be 1. Then Jane Smith also happened to map to 1. So we took the hash, mod the number of buckets, also got 1. But when we checked that bucket to add the value for this key, we saw that it was already full. So we can't add it there. So what we do is we just go to the next bucket sequentially. So bucket 1 was full, so we go to bucket 2. We see that it's empty. We add the item to bucket 2. So then to retrieve the item, you have to do the exact same algorithm. You take the hash, you find the bucket. If the object is not in that bucket, you have to iterate sequentially until you find the object you're looking for. Yeah?
Now, will the hash value be different because of that, or will it still be the same? It'll just know to go look at the next bucket.
It's a good question. The hash value will always be the same for any given key with a good hash function.
So John Doe and Jane Smith will say 1 for that bucket, even though the information is really the same.
So don't get the hash value and the bucket it's mapped to confused. The hash value is actually only the result of this operation, and then the bucket it's mapped to is the result of this whole operation, including the mod n. So the hash value should always return the same number for any given key, whereas the bucket that it's mapped to is entirely dependent on how many buckets there are. So if we had 16 buckets instead of 8 buckets, it's very likely that John Doe and Jane Smith would not map to the same bucket because we're taking a different mod. So to retrieve, again, find the bucket, take the hash, mod n. If it's not there, we have to iterate successive buckets until we find the object we're looking for. That means that you have to save the key and the value in the bucket, because otherwise you don't know if you're retrieving the right value. I'll repeat that again because it's important. You have to save both the key and the value in the bucket. So if our hash table looks like this, and we're trying to retrieve Jane Smith, we take the hash of the key Jane Smith, we mod the number of buckets, we get 1, we check bucket 1, and we see that the key saved there is actually John Doe. So we know that the value saved there is not what we're looking for. So then we iterate, we find bucket 2, we see that the key is Jane Smith, we know that we found the right key, so we grab that value out of the bucket, and return it. So that means in your hash table implementation, you will be saving tuples of key value pairs in your buckets. And again, your bucket will be an array, which you can use a Python list. And it's the same thing because Python lists give you constant time access to an element at an index. Yes, Josh? In a bit. But generally speaking, you want to have like, once 2/3 of your buckets are full, you want to reallocate new buckets. But there's a reason for that. We'll talk about that in a second. Yes, Ignat? Right. So how does it know that when there's a collision that we're retrieving the correct object? The answer is we have to save both the key and the value in the bucket. So then when we're searching the buckets, we have to compare the key that we're looking for with the key that's saved. And when we find that they're the same, we know that we found the right value. Yeah. So Ignat is thinking about complexity. What if our hash table is totally full and our buckets are full and there's tons of collisions? Maybe we don't actually get constant time access like we want. Maybe it's O(n), so we'll talk about that in a bit. So dict does this. In the Python, the dict, it's actually a hash table. It's implemented in C. It's all open source. You can go look up the code. So we're using PyC, which means that a lot of the code and fundamental elements of the Python language are coded in C for speed, which is nice because you get sort of some of the advantages of the speed of C without ever having to write any C yourself. So dict does this. Dict in Python does linear probing. So when there's two input keys that map to the same bucket, it will search through sequentially until it finds an empty bucket and add it there. So this also means that if you want to implement a hash table with linear probing, you have to be careful because when you get to the last element, if you increment again, you'll have an off by 1 error, you'll be out of range. That's a crash. Instead, when you get outside this, you want to loop back to zero. And there's some other considerations and snafus that you'll find if you implement a hash table with linear probing. Eliel, for example, I know did this, and because we were looking at the code, there's a lot of like edge cases that can happen, so you have to be very careful. Okay, so now there's a second way to resolve collisions, and it's called chaining. So instead of storing the data directly in the bucket, actually, each bucket is a linked list. So you have an array of linked lists, and then when something maps to the same bucket, you just append it to the end of the linked list. So this is why it's super important you know how linked list works, because when you implement your hash table, you're going to implement it with chaining, and you're going to have an array of linked lists. So you're going to create both the hash table implementation and the linked list implementation, and you're going to use your linked list as part of your hash table. So what does this mean? If there's a collision, you just append it to the end of the linked list. And to retrieve the item, you have to find the bucket, and then you have to find the element in the linked list. So you're still storing key value pairs in the linked list so that you can know when you found the correct item. Does this make sense? Any questions about chaining? Yeah, Mike.
Could you give us an example of a situation where chaining may be advantageous over linear, or vice versa?
Yeah, so chaining and linear probing have different behaviors depending on the load factor, like how many elements are in your linked list and how many buckets you have. So I think that is this. So we will talk about that now. So load factor is a very simple calculation. It's just the number of entries divided by the number of buckets. So if you have 76 entries in a hash table with 128 buckets, then that's 76 divided by 128, or 0.59375. That's your load factor. So let's talk about how chaining and linear probing behave differently for different load factors. Here's this chart here. Collision resolution affects the performance of your hash table. So whether or not you choose to do linear probing or chaining is important. In linear probing, let's take the example where you have 8 buckets and you have 7 elements already in there. If you want to add another element, there's a very good chance you're going to have to iterate every bucket. So that means adding is no longer constant time. That means it's end time. So that means your performance for retrieving and adding items to your hash table decreases as the load factor increases. And it actually increases asymptotically. which means with linear probing, once your hash table is full, you can't actually add any items anymore. It's full. So that means your performance is so bad as to be infinitesimally bad, which is why this line here is asymptotic to the y-axis. It will never actually intersect. You can never actually add an item to a full hash table that uses linear probing. So that's bad. So that means you have to be very careful if you're going to implement a hash table with linear probing, like the Python dictionary. You have to be very careful to actually grow the size of the hash table when it's beginning to get full. So we'll talk about that in a second. But we can see here that linear probing is actually more performant for most use cases compared to chaining until you get to the point where it's beginning to get really full, and then linear probing becomes so bad as to be unusable. Yeah, Adrian.
So that's where the 2/3 come.
So this is where the 2/3 come in. If you look here, 2/3 is around here where linear probing starts to get exponentially worse. So that's why when your load factor is around 2/3, like 2/3 of the buckets are full, that's when it's time to basically add more buckets and redo your hash table. So we can see chaining gets worse linearly. So as more elements, as the load factor increases, chaining, the performance of adding and removing elements decreases linearly, but it never reaches the point where it's impossible to add items. So if you have 50 elements in an 8-bucket hash table, maybe each bucket is full, but it can't actually be totally full because remember, it's a linked list. And linked lists you can always append to the end, and that memory does not have to be contiguous. It can be added anywhere. So your chaining hash table can never actually be truly full, but just like with linear probing, the performance will decrease. So we can talk about what if you have a hash table with 1 bucket and you're doing chaining. At that point, that hash table is actually just a linked list, a single linked list. So adding and retrieving items to that hash table is actually a linear operation. It's big O of n time, not big O of 1. And the whole point of hash tables is that we're trying to achieve big O of 1 time, constant time access and deletion. So any questions about load factor and how load factor affects the performance? Okay. So once we get about to 2/3 for linear probing, it's time to resize the hash table. So how do you do it? Well, it's similar to allocating a new array when you have a dynamic array. Basically, you will generate new buckets. So if you have 8 buckets in your hash table, maybe you'll generate 16 buckets. So maybe you'll double the size of the hash table. Then you have to go through every element that you have stored in your old buckets, and because the n number, the number of buckets you have is different, that means each item will actually hash to a different bucket now because you're doing mod 16 instead of mod 8. So that means when you resize the hash table, you have to iterate through every element and redo the hash operation, redo the mod n operation, and stick it in a new bucket. But it can be done in Python in about 4 or 5 lines of code. It's pretty easy. Basically, you just do a for loop for every item, key value pair in your hash table, generate the hash again based on the key, do the new mod 16 instead of 8, and then assign it to a new bucket. And then once you're done with that, you just reassign the main pointer that points to all of your buckets to your new buckets. Does that make sense to everyone conceptually? You're going to have to do this. Okay, you don't have to because you're going to be using chaining, but it's a good optimization to do this for your hash table. Yeah, Alan. Yes, the new size does affect the performance. So if you have twice as many buckets, you have on average half as many collisions, which means that access time will be maybe like twice what it was before. But there's a trade-off, right? You have to use more memory. So your hash table will grow in size. And you can get to the point where your hash table is 10 million buckets, and maybe at that point you should be using a database or some other data structure. Yeah. So the number of buckets, there's like another super fancy optimization where instead of doing linear probing, you do this thing called double hashing, where you jump kind of randomly. And in that case, you need to have a prime number of buckets because of some mathematical features of how the double hashing algorithm works. In general, if you're doing linear probing or chaining, it's just easy to start with like a power of 2 number of buckets and just double it every time. So the Python dict, I think, starts with 8 buckets. And I said it does something similar to linear probing. It actually like randomly picks the bucket in a repeatable way, which is crazy. And you can do it too if you want, but you have to always have the same seed in your random number generator. That's a whole other thing. But linear probing is much easier and has similar performance, if not quite as good. Yeah. Okay. So now it's time to talk about the complexity of hash tables. So we have an average case and we have a worst case for each one of these. So the worst case is like where your bucket is full and the load factor is 1, right? So space. This is a new concept. When talking about complexity, you usually talk about the time it takes to do an operation, but also very commonly we'll talk about the amount of space a data structure occupies, because there are trade-offs there too. Very often, if you occupy more space, you can do things faster and vice versa. That's like a common trade-off in data structures. So on average, what is the amount of space that a hash table will need to take? You can use the same exact big O notation to talk about space. Any ideas? Yeah, Nick? O of n. Yeah, why is it O of n? Yeah, more pointers as a constant number per n. So for example, if you have to allocate like 5 pieces of memory for every item, then that's 5n space, but the n overwhelms the 5 and it's still big O of n. So that's correct. On the average case, you're going to need O of n space, like 1 unit of space for every element added to the hash table. That's the same for both linked lists and for linear probing. Because in linear probing, it assumes that you're going to resize the hash table once it's full, which means you're going to need at least 1 bucket for every element in the hash table. Okay, what's the worst case space? Well, if you were being really weird and goofy and you were making some hash table that allocates like additional memory, like every time, all right, this is a contrived example, but if you allocate n amount of memory for every element that's added, suddenly n amount of memory for every element, which is also n, is n squared. So if you were being crazy, you could devise a hash table that has n squared space complexity in the worst case, but we're not being crazy. We're talking about like just the standard vanilla hash table. And the worst case for a vanilla hash table is the same as the average case. It's going to be big O of n space required per element. If that little bit was confusing, you can just ignore everything I just said, throw it out of your mind. It's not super important. All right, this is more important though. What is the average case time to search for an element in a linked list? Yeah, Nick? O of 1. Why is it O of 1? Right. Right. So when talking about average case versus worst case, we assume average case is like a nicely set up hash table, which means that either it will map directly to the bucket or it'll map to a linked list, but we only have to search a small amount of things, like a constant number of things. So on average, searching a hash table is constant time, big O of 1. And this is like the most important thing about linked lists is that they're about hash tables, is that there's constant time access. So that's why they're very powerful. That's why you're using them to count how many words are in a corpus, because when you have a corpus of 10 million words, you want to be able to increment the number in your histogram in constant time, not in n time. Okay, so what is the worst case search time for like a hash table that is full, basically? Yeah, Nick? O of n. Why is it O of n? Right, so either your hash table is full or all of your items are in one bucket. So the very worst case, all of items in one bucket means that you're actually just using a linked list data structure, which means it will take linear time to search through that linked list to retrieve the item. Does that make sense? So it's the same as just using a plain linked list. Yeah, Isabel. Right. So it's not necessarily the first one, and it also depends on the number of buckets. So if you have, say, 1,024 buckets, and each of those is a linked list, the odds that everything maps to the same bucket, assuming you have a good ideal hash function, are basically 0, because an ideal hash function will map randomly to any number between 0 and 1,023. So that means retrieving an element, if all the elements are distributed uniformly, when you map to a bucket, you're just throwing away like 99.99% of all the elements that you have to look at, and you're only looking at the ones that map to the same bucket, which will be a small number. Yep, time complexity. So this is like kind of theoretical time complexity. Actual runtime depends entirely on the number of buckets, the number of elements in the buckets, and how you're doing collision resolution. But when we're talking about theory, and we talk about the worst case, we're kind of talking about the situation where everything maps to the same bucket, and actually that means it's a linked list data structure, and you have to search through every element to find the key and the value.
Is there any case where it's not that worst case that it would be open? Like if it's not just a linked list, like if it's it just has a lot of collisions, would that
Right.
be open?
No. In that case, it would still be constant time. It's a good question. Okay. So how about inserting an element? What is the average case runtime? I'm not going to call on Nick again. Yeah, Iman. O of 1. Why is it O of 1?
Because the hash function on average will give me the
Right. So on average, if there's no collision or small amounts of collisions, the hash function will take you right to the bucket where the item is stored, and you can just retrieve it instantly. And you can do that because, again, the buckets are a contiguous piece of memory. They're an array, which means you can index into them instantly without doing any searching. How about the worst case for inserting? Yeah. O of 1. Why O of 1? That's true. But remember, this is the worst case, which means actually, for example, a worst case scenario would be everything hashes to the same exact bucket. Okay, so this is where it gets a little fuzzy. If your linked list has a tail pointer so that you can append to the end in constant time, then it would be constant time. If your linked list does not have a tail pointer, you have to iterate through to add something to the end. So that's a good point. It would be constant time with the tail pointer. Without it, it's end time. So there's all these kind of assumptions we're making when we talk about this. And so that means in interviews, you will always be asked to analyze the complexity of the code that you just wrote on the board. That means you might want to ask or make clarifying statements about your assumptions when you give the runtime complexity. Because, for example, having a tail pointer in your linked list will change this linear complexity to constant. So it's very important. Yeah, Ignat. Why can't you append to the beginning of the linked list?
It's still the same bucket.
You can. It is the same bucket. There's no reason you couldn't. That would be O of 1 also. That's another one of those clarifying statements that you'll have to make when talking about assumptions, because kind of the theoretical hash table appends to the end of a singly linked list with only a head pointer. Okay. So how about deleting an element? What is the average case? Well, actually, the average case for deleting an element is the same as search and insert. It's constant. Because you can find it, then you just reassign a couple pointers, and you're done. How about the worst case? The worst case is also the same as search and insert. The worst case is you have to search through every element in one bucket where all the elements are stored in a linked list to find the one you want to delete. Okay. So let's talk about, in most cases, you're going to be using strings as the key for your hash table, because the key is going to be the word, and the value is going to be the amount of times that word appears in your corpus. So let's talk about a very simple string hash function. Strings are a list of characters. Characters have numerical values. So if you've ever looked at an ASCII table, every character is a value between 0 and 255. We no longer use ASCII because it doesn't include a ton of characters from other languages. Now we use different character mappings. But every character has a numerical value. So what if we had a hash function where we just added up all the characters in the word, and then that was it? So like, for example, if like D had the value 5 in the ASCII table, it doesn't actually, I'm making this up, O had the value 10, and G had the value 15, we could add those up. 5 plus 10 plus 15 would be 30. So dog would hash to 30. There's our hash. Yes, Ignat?
So would God.
So would God. But dog is the same as God. And now we don't know what to think, because our gods are dogs and our dogs are gods and everything is wrong with life. So that's why this hashing algorithm is called the lose-lose algorithm. It's like the worst string algorithm you can do, but it's also the simplest, and you can kind of understand conceptually what's happening. If you're interested, there's a good and still fairly simple string hash algorithm called DJB2. So you can search Google DJB2 hash, see how it works. It's kind of cool. It uses like some prime numbers to try and ensure that the numbers are mapped randomly among the output space. But actually, when you implement your hash table, you won't have to implement a hash function. You can use the built-in one that Python provides. So if you're interested in how hash functions work, look up DJB2. It's a simple, good one. Don't ever use the lose-lose algorithm because it's terrible. Yeah, Ignat. So you're right. You actually, like if you look up DJB2, it does use the character, the numerical value of each character as part of the hash, but it's more complicated than that. It uses some prime numbers. So if you want to know the time complexity of various Python data structures, including list, dec, and dictionary, you can go to this link here. And it will tell you a little bit about how each of those data structures are implemented, and it will tell you the time complexity of them so that you can make good decisions when deciding which data structures to use, and you can see what the underlying implementation is. All right, so that's it for hash tables. Any final questions? Okay, thank you.